So thank you very much, first of all, for inviting us again to your nice seminar. And so we will report on some joint work we did recently. This is also in collaboration with two more PhD students from Munich, Alexander Glikovic and Antonia Paraskevopoulou. So they're covering two papers that appeared in September. And on the left, you can see, by the way, if you haven't heard it yet, so our new building. So our institute has been moving from our former location now to the campus of Garching in this nice new brownish building that you can see here. Okay, so that's how it goes. Okay, so let me start more general conceptually. So as a matter of fact, historically, I think we have been witnessing how to explore quantum gravity from a sort of perturbative point of view, from one of its perturbative corners. And if you recall here this duality star from the 90s, what was written at these corners here, at these edges, is actually something that would now be called at infinite distance in moduli space. In fact, here is the dilaton that goes to infinite or to infinite distance. And so maybe we can sort of have a new look at this picture by taking our recent understandings of the swampland conjecture, some of the swampland conjectures into account, and mostly those dealing with infinite distance limits. And I don't know whether I have to record this. So there's a swampland distance conjecture telling us that if you approach infinite distance limits in moduli space, towers of states become light. This has been more refined by this nice work by Lerche and Weigand, and it's called the emergent string conjecture, that essentially only two special limits can occur. In one case, if a fundamental string, or if at least this theory is dual to the theory of a fundamental string becoming the lightest state and the tower becoming light. And there's the decompactification limit where these light states are in some sense dual to a KK tower. And these will be the lightest states. And moreover, we have been told by Giadvali that in the case where you have a large number of species, which actually happens to be the case in these infinite distance limits, the quantum gravity cutoff is actually not the initial Planck scale, as you might have thought, but there's a scale below the Planck scale, which is called the species scale. And which will be the main topic of today's talk. There's also in this realm of conjectures about infinite distances, the emergence proposal. And references I will be given later. Sorry, on the next page, I have more on this in detail. And so this will be the main topic of this talk and how this might be related to all these other conjectures, and to make it in particular an attempt to make it precise. Okay, so let's start here maybe with this type 2A M theory corner of this duality star, just to give you a flavor of what we are thinking about. So if you now go to infinite distance here, say you send the dilaton to minus infinity, which means that the string scale actually goes to zero or becomes small. So this is the usual string theory that we all love and is covered in textbooks. So where the lightest towers of states are the fundamental string excitations. And moreover, if you now compute the species scale for the setups, this indeed will turn out to be the string scale. And of course, we know that there are additional states here, the D-brane states. And so these are non-perturbative states. And if you express their mass scale in terms of the species scale, which is the string scale, you find that they have this non-perturbative behavior in the coupling or in the parameter that goes to zero in this infinite distance limit. So from this, we take that usually we consider this as a perturbative quantum gravity theory, where the perturbative degrees of freedom are the string excitations, and these D-branes are sort of classical configurations, which maybe you can think of as coherent states of the fundamental strings, like what you do for the boundary states, for instance, describing the D-brane in CFT. Okay, so this is the familiar story, but of course, in the type 2A dilaton moduli space, there's another infinite distance limit, that is, if you send phi to plus infinity, you go to strong coupling. And we have been taught that this is a decompactification limit where a new 11th direction opens up. And the big question is how you describe this perturbative quantum gravity theory that is, when you expand it, in the 1 over this very large parameter that you naturally have here, which is the size of the 11th dimension. So here there's also a natural small parameter, which plays, so to say, the role of GS, the string theory limit. And moreover, the lightest states, as we will see or recall again, in this case will be the D0 branes or the KK modes along the 11th direction. And when you compute with these towers, then the species scale, you find, of course, that this is the 11th dimensional Planck scale. But then the question occurs, okay, so can we also make sense of perturbative and non-perturbative states in this peculiar large distance limits? This is an open question. That's not so clear. Is it just that the D0 branes are the perturbative states and all the other stuff is non-perturbative? Or how should we do it? And what we will see, or what we'll argue, is you should do it. You should consider this cutoff here, the quantum gravity cutoff, as the relevant scale. And you should call, or this is our proposal, all states, all towers of states with a typical mass scale of the tower equal or below the species scale. This you should include into your fundamental degrees of freedom, your perturbative degrees of freedom, and all the rest as non-perturbative. Okay, so that's sort of behind what we will be doing on the next slides in more detail. But of course, the ultimate question is, okay, these are just perturbative limits. So what is actually the quantum gravity theory here in the bulk at order 1 couplings, where the cutoff scale will be actually, in this case, the 10-dimensional Planck scale? And there have been recent attempts to get at least part of the information on these theories. So this is the ultimate question, whether we need a completely different formulation of quantum gravity or whether we can still use our intuition of string theory or M theory to get an idea what this theory actually is. Okay, so now coming to the emergence proposal. This was actually our main motivation behind this verse. So the initial trigger, we wanted to understand, so to say, more generality, what Irene, Aaron, and Thomas Grimm, and also the group around Heidenreich, Ries, and Rodriguez meant by the emergence proposal. So here I'm just recalling from the review article of Aaron, what he called the strong emergence proposal. It says, this is really a citation, the dynamics, kinetic terms for all fields are emergent in the infrared by integrating out towers of states down from an ultraviolet scale, probably the species scale, which is below the Planck scale. Okay, so this sounds rather generic, I would say. So what is meant by that, or what do they mean? I mean, they did a couple of nice computations, and they do sort of a quantum field theory. They use into quantum field theory intuition, and they really mean that if you integrate out these towers of states in loops, say at one loop level, you have a chance to find again back at best the full kinetic terms, or at best the tree level terms. And this, they showed that by doing a certain approximation, so they were summing the towers of states which were light in certain limits up to a maximum number where the mass of each individual state was actually below the species scale. So they were not summing up these light towers up to infinity, but this was just an approximation they were doing, so to say, to justify this, probably to justify these quantum field theory formulas. And what they found is, and this was nice, that the leading order behavior, at least the scaling that depends on the moduli, the scaling was precisely the tree level behavior. Of course, the numerical prefactors were not 100% right, and in principle there could be corrections, but this was just meant, as I understand, as an approximation to give you a flavor of that such an idea could work. Okay. So what we will now try to do, or what our motivation was, to see really, I mean, if this is really a concept of quantum gravity in general, of course, there should be a full embedding of this concept into string theory or quantum gravity. And this is what we were heading for. We wanted to see whether we have a well-controlled setup where we can make these computations more precise in the sense that we really sum up the full tower of states up to infinity and to see what we get. So for that purpose, we considered the well-controlled 4-dimensional n=2 vector multiplet moduli space, say for type 2a on a Calabi-Yau, because many things are known for that moduli space, and we could do some checks. And to summarize already our findings, this is a proposal still, I mean, Still there are gaps, but what in the moment the picture we are having is that the effective action of M theory, so in this decompactification limit on S1 times some Calabi-Yau, say, with b dimensions, emerges by integrating out the full towers of states up to infinity, whose tower mass scale is below the species scale, which in this case is the Planck scale in one dimension higher, so when this S1 decompactifies. And these light states are transversal to the S1, M2, M5 branes wrapped on X with KK momentum along S1. So these are the D0 branes. So from the type 2A perspective, these are transversal. So these are D2 branes, NS5 branes, and D0 branes. Okay, so we will see that we have some little evidence from 1/2 ppr saturated amplitudes that we have good control over. And moreover, if you, in terms of the natural small coupling in that limit, which is 1 over the size of the 11th direction, this is sort of the parameter in which we expand. The other towers from other branes, they have masses, if we express them in terms of the species scale, that look like non-perturbative in that sense. So this would be, for instance, M2 and M5 branes wrapping the S1 direction as well. And we will see that actually the computation we are doing is very close, and there's a lot of known in the literature, close to the M-theoretic computation of Gopakuma-Waffa invariants, and also R to the third terms by Green, Goodperle, and Van Hove, which have also gained some attention recently in some recent papers. They are of the same type. Okay, so now more concretely, so we want to consider type 2A on a Calabi-Yau and consider the Kähler moduli space of that. So in the first part of this talk, this is now the part that I will cover, we look first just to get some experience and to see what we can expect. We take the limit where we have an emergent string. So for that, we need a K3 vibration, and the limit in moduli space, Kähler moduli space that we are taking is that the base of this vibration, we are scaling big. So with lambda is the scaling parameter that is large. And of course, we don't want that. So this is effectively a 4-dimensional effective theory that you get, but we don't want to decouple 4-dimensional gravity. So we have to do this limit such that the 4-dimensional Planck scale scales constant. So we have this what is called co-scaling limit, where also the string coupling goes to infinity. So we are on a strongly coupled, when we go to this specific limit in Kähler moduli space in this co-scaled way, we are at large string coupling. Of course, this is precisely the limit for which there's this famous type 2A heterotic duality. Indeed, there will be an emerging string here, as we will see. This will be a wrapped NS5 brane on the K3. But luckily, in this situation, we have a dual description in terms of a heterotic string, where we have a nice correspondence. So we can have some checks. So we can check what terms in the heterotic dual are actually what we might call emerging via loop corrections. And then the second part, this will be done by Niccolò. The more interesting, maybe, story is about now we are going to another limit where we have this isotropic scaling, where all Kähler moduli scale isotropically with the same scaling with lambda, again, in a co-scaled way to keep the 4-dimensional Planck scale finite. And then you get here also that you have to go to strong coupling. But this limit is, as you can see, is precisely the 5-dimensional decompactification limit, where type 2A on the Calabi-Yau decompactifies to M theory on the Calabi-Yau. So this is the decompactification limit that we get. So we are about to learn something about M theory from here. Yeah. And the good thing about this here, so you see this moduli space looks very much like the former M duality star that I was showing to you. And in fact, there's a similarity, of course, in the sense that we have this infinite distance limit. But here the nice situation is, what was different from before, that in this moduli space, we also know the desert, we also know the bulk, because we know the prepotential, certain quantities, topological quantities, we know exactly from other methods by going actually to GS small and then applying mirror symmetry and so on. We know that the prepotential has a sort of, for concrete Calabi-Yaus, we can compute the expansion, and there will be a cubic term given by the intersection form of 2 cycles on the Calabi-Yau, and a constant term, plus non-perturbative terms that are governed by the so-called Gopakuma and Waffa invariants. Okay, you have similar expansions for F1 and F2 for other topological quantities. So F1 is, by the way, precisely the coupling that is also related to the species scale in the recent works. Good, so this is our setup. So let's talk about the emergent string limit first, just to get a flavor. Luckily here, there's so much is known here that it's just a repetition of known results, but maybe with a new interpretation. Okay, for sure, let's go one step back. Since we know the exact results, so if we are going on to a specific limit and, so to say, write down a new perturbative expansion, eventually we are doomed to rederive the exact result. Otherwise, we would not have understood the perturbative limit. No? So we are doomed to reproduce the full exact free potential in a perturbative expansion. And the question is how? So let's consider the K3 vibration as the K3 vibration. This is maybe the simplest one, which has H11 equal 2. And this is also the model that was first used when this duality to the heterotic string was proposed by Ketchrew and Waffer. And here the prepotential is indeed exactly known from mirror symmetry. So there are two Kähler parameters now, and say T2 is the one which measures the base. So there's a K3 vibration over P1, and T2 measures the size of the P1. Then the prepotential is given in the following way. So these two terms here is just the intersection form. Then there are non-perturbative terms which, though, do not depend on T2. They only depend on T1. And then in general, there will be non-perturbative terms also depending on T2 and also on T1. So I was ordering these terms already in hindsight of what will come next. So now the question is, since we're doing T2 now, so T2 is going to infinity now. Sorry, T2 is going to infinity. So now here we have already an expansion for large T2. Now. So this will be the leading order term. This will be subleading next to leading order. And this will be even exponentially suppressed in T2. Okay, so now the question is, so what are the towers of light states in the T2 going to infinity limit? Well, if you go to the list, what's happening there? So first of all, one can wrap NS5 brane on the K3 fiber. This yields a 4-dimensional string, and you can compute the tension of that string, depending on the scaling parameter lambda. And so the excitations, we expect these excitations to have a typical mass scale, which is the square root of that tension. So this will scale with m Planck over square root of lambda. Moreover, for a string tower, we expect the species scale to be exactly the same as the string scale, at least if there are no lighter states, no lighter towers of states in the theory. And now you're going to the list of other excitations, then you find a couple of particle-like de Bruijn excitations in 4 dimensions which have the same parametric mass scale, but no parametric scale that is lower than the species scale. So in particular, you will have D0, D2, and D4 branes, all wrapping only cycles on this still left small K3, so avoiding the P1 base, of course, because if it would wrap, it would have a large mass because it has high tension and large size. And moreover, you can see KK modes on the P1, and P1 is large, so these KK modes can be light, but their mass will also scale like m Planck over square root of lambda. So there are a couple of extra states besides this tensionless string or light string that will also become light at the same rate. So proposal again is that we have to include all these states in the perturbative description. And this is precisely what is done in the heterotic dual model, because here we luckily have this heterotic dual, and there's a precise map in this case. The details are a bit intrigued here because it's a very special point in the T2 moduli space where we first get an SU2 enhancement and then we Higgs it and so on, but it is not so important here now. Important is that we have a precise map of the objects on the type 2A side and on the heterotic side. In particular, type 2A will gauge fields are mapped to the heterotic gauge fields that come from the T2 here. The vector bundles on K3 and so on, they are completely Higgsed. Sorry again. Then the wrap type 2A 5 brane, which is the emerging string, is of course mapped to the heterotic fundamental string. Then the other type 2A wrap D0, D2, and D4 branes are mapped to the heterotic KK and winding modes on T2. And these are also the things that are charged under these gauge fields here. And the KK modes on the P1 are mapped to heterotic KK modes on K3. And this is all consistent with also the moduli map that sends the size of the P1 base on the 2A side to the four-dimensional dilaton on the heterotic side, and the other Kähler modulus is mapped precisely to the Kähler modulus of this T2 factor. And now people have been sitting down already in the mid-90s to compute at least part of the heterotic prepotential, in particular this one loop correction here. So this is the gauge threshold corrections where you have the methods to compute them. Again, 1/2 BPS states will contribute. And you find, or these people found, that the emerging one loop correction first satisfies this sort of second derivative satisfies this relation, but if you integrate it, it precisely matches the type 2A contribution G1 here. So this indeed is dual to the heterotic one loop correction. And the heterotic one loop correction is, of course, the object where on the emerging theory now, you are integrating out, you do a one loop computation, and you do the one loop computation in a string theory. This is known how to do it. We know how to compute this Schwinger diagram. We now do know how to regularize it. So we integrate over the fundamental domain of the torus and so on. So this is what you might want to call emergence. So the lesson here now is that from the former type 2A tree level terms, there were just two in the intersection form. This one here, which is leading order for large T2, this remains also tree level in the heterotic string. The other one indeed becomes part of the one loop correction in the heterotic string. So this you might call emergent. It comes out from a one loop computation. So we would say that at least in the setup where you include only those states, or you include in the emergence computation in this one loop diagram, the towers of all states with a mass scale below the species scale, then only the second term here is emerging. So all T2 independent terms in particular are not, only the T2 independent terms are emerging, and the other ones are not emerging. Yeah, and this is clear as none of these branes states that you have that can sorry, I'm always touching that can run in the loop. Neither of them wraps actually the large P1, so is sensitive to the modulus T2. Okay, so just a comment. So now when you compute G1 and you interpret the contributions that you know to exist from the heroic side in terms of the type 2A variables and objects, then you come to the conclusion that G1 of T1 does indeed receive contributions not only from D2 D0 bound states, but also from excitations of NS5 D2 D0 BPS bound states. This is simply because on the heterotic side, this is a 1/2 BPS saturated amplitude, and the 1/2 BPS states in the heterotic string include KK winding, but also left moving string excitations. And the left moving string excitations, some of them are dual to the wrapped NS5 brane. Okay.
Ralph, can I ask already on this? Like, so what is your take on this or interpretation, like about the tree-level term? You think
the tree-level term is
from strings, I don't know, like we could try to get it from integrating strings, but it's not a computation that we know how to do because it's already like the tree-level string axiom?
Well, I would say that for an emergent string limit, if you only integrate out the states, the towers of states up to the species scale, you are missing some of the tree-level terms. You are not getting them via these loop corrections. They are still tree-level. I know there was the idea of Aaron that maybe then you have to increase the scale and integrate out more stuff. Of course, this we cannot say, but I think this recipe might work, but I think it's not natural, I would say, because then you are giving off this very special scale that is known to exist, which is the species scale. And some of your some of the states I would call non-perturbative here. When you talk about the heterotic, a fundamental heterotic string, so you would say then that some of the non-perturbative states, D-brane states, from the not D-brane states, NS5 brane, wrapped NS5 brane states, for instance, in the heterotic string theory now, you would also include them in the integrating out process. But this, I think, is very unnatural, because usually we think of these in these limits, and this is a certain recoupling limit, we think of these states rather as being composite. These are classical. These are coherent states. These are classical field configurations. So
yeah, I guess the question is, what is the scale? Because what we had in mind is that has to be the scale where gravity becomes strongly coupled. So that's easy for the Kaluza-Klein, like the compactification limits, because it's just the species scale. But in the string, yeah, there's always this question, no? That, I mean, it seems different. If you identify the species scale with the string scale, it's not really that gravity becomes strongly coupled. So yeah, okay.
Yeah, but this is yeah, well, I cannot say more. I mean, I think there is the only loophole, I think, is that you increase the scale, but which states you integrate out.
Okay.
Now, this is, I think there we have complete agreement on, but I still think that it's unnatural. But
okay.
Because here we are in a special situation, we have really a true fundamental string that we completely understand. And we never integrate out stuff. We never integrate out fundamental objects like strings and D-branes at the same time. Yeah. Would be a completely new theory. But that's the only possible loophole. And I see in the moment, or we see in the moment. Of course, everything is still in progress. It's not that we have a final big picture, but we are collecting evidence, I would say. Huh? So I have 2 more slides, if I may continue. So let me start now with the discussion of the decompactification limit, when Niccolò will then continue and give you more details. At least I would like to show you, again, this analysis of the light states in that limit, because this is really parallel to what we discussed for the erotic string, for the other limit, for the emergent string limit. Okay, so now we consider this isotropic scaling limit. We don't need any vibration for that. We can also do it for the quintic and so on. So every Kähler modulus is scaled in the same manner, with lambda going to infinity, and we have the co-scaling such that the 4-dimensional Planck scale is constant. And then using the relations between type 2A and M theory, you can see that this corresponds to the decompactification of one direction, that you get M theory on the same Calabi-Yau, where the volume measured in units of the 11th dimensional Planck scale stays finite. Good. So the lightest degrees of freedom, as Irene was already alluding to here, are KK modes, or in this case now, if we come from type 2A, are the D0 branes. And we can have bound states of these D0 branes, and their mass scale, and if expressed in terms of Planck, scales with lambda, like a lambda, with power lambda 3/2 in the denominator. And now you can, this is just a standard 1-dimensional KK tower. So we can use our standard 4-dimensional relations for the species scale for such a tower. And then you find that the species scale is M Planck over lambda to the power 1/2. So you have really a couple. So this is parametrically larger than the mass scale of the D0 branes. And this is indeed the 5-dimensional Planck scale in addition. Okay, so if we now follow our recipe, that we should not only integrate out the D0 branes, but all the towers of states that have a mass scale below the species scale, then there's room for additional towers to be lighter than lambda tilde, because I mean lambda tilde is parametrically larger than MD0. And indeed, you can find a couple of towers that have the same scaling as lambda tilde. And these are, for instance, D2 branes wrapped on the 2 cycle on the Calabi-Yau has the same scaling, as you can see here. Moreover, D0 and D2 branes, these are precisely the objects which are electrically charged under the graviphoton and the gauge fields residing in the N=2 vector multiplets. So these are the objects that can contribute in loop diagrams. Then we have also KK modes along the Calabi-Yau, which also have the same scaling. And still, we have NS5 branes wrapped on any of the 4 cycles on the Calabi-Yau. There can be no more than 1. And if you just do the math, the string scale is again a Planck square over lambda, whose square root, which is the mass, the expected mass excitations, also scale like the species scale. Now that here we would be witnessing, so to say, emergent strings. I mean, not just a single one, but H11 emergent strings, but they have a mass that is higher than the lightest state. So I think this is still allowed by the emergent string proposal. But the KK modes and the NS5 branes, they are neutral actually. Obviously, they are neutral under the gauge fields in the vector multiplets, which comes from the C1 form and the dimensional reduced C3 Ramon form. So they do not directly couple to them, but if there are bound states of them with the D0 and D2 branes, and indeed there are bound states, they do exist, half BPS bound states, they might also contribute in loops. At least we see no reason why they should not. And if you now express the masses of all the other states that I haven't mentioned in terms of the species scale again, then you find that they look non-perturbative, where GM is again the natural small parameter, which is 1 over lambda. And you can view this as classical or coherent quantum states. This is our proposal. Okay, so this is more like the picture. And now Niccolò will tell you the details why we come to this conclusion and how integrating out precisely these towers of states, of BPS states in loops, gives you tree-level results that we know already exist. Okay. So this
Sorry, can I ask a question?
Yes.
Yeah, so in this decompactification limit, the units, the volume of the Calabi-Yau in the units of 11D M theory, is that small or large?
The volume, no, this doesn't matter. I mean, the volume, let me see. I mean, the volume.
So the volume of Calabi-Yau in the units of 11D and Planck.
Everything is expressed. I mean, you can express first, of course, in terms of MS, but then if you use the relay. So what happens in this limit is that that the volume of the Calabi-Yau in units of the 11-dimensional scale, which is M11, this stays constant under the scaling. This doesn't scale, so this is finite.
I see.
And only the 11th dimension grows.
So because I mean, if this volume is much bigger than the 11D, like in the units of 11D and Planck, if it's much bigger than 1. Then I would say the lambda species is the 11D M Planck, but it's not the 5D. But you're saying that you're only concerned in the scaling relation, right? And
the scaling, absolutely, the scaling. Yeah. I mean, and the scaling, by the way, the scaling of the 5-dimensional Planck scale is actually the same as the scaling of the 11-dimensional Planck scale.
I see.
This we have checked, so there's no difference.
Thank you.
Yeah, welcome. Yeah, are there more questions now? I mean, we can also ask later, of course. I mean, but this was more like the picture. I mean, it will now be filled with more details in the next part. Yeah, so then I stop Sherman.
Yeah, you can.
Yeah. So I stop and so that Niccolò can take over.
Okay. Okay, so just let me thank very briefly the organizers once more. It's my pleasure to accept this invitation. And so we'll just continue where Ralph stopped. Let me summarize a few points which are relevant and important to be recalled. So the motivation for this work is that one of the motivations is that the precise realization of the emergent proposal in string theory and quantum gravity is still unclear. And Ralph just argued that there are some possible obstruction in realize it exactly in the emergence limits, at least in the way he presented. And now for the rest of the talk, I will give evidence that instead there can be hope for the decompactification limits, for certain decompactification limits. And to reach this conclusion, it will be crucial to include in loop integrals infinite towers of states. So I will stress this point later that if you have a sum of states, you should not cut the sum off at a certain level, as you might naively want to do from QFT reasoning, but it will be crucial to include infinite tower of states. And the tower of states to be included are those which Ralph explained. So there is this criterion that we have to look at the mass gap of the tower and check whether or not it's parametrically larger than the species scale. Okay, so for the rest of the talk, I will just consider the setup Ralph already introduced. So step 2A on Calabi-Yau, and I will work on the Kähler moduli space in a specific decompactification limit, which is an isotropic limit for the Kähler moduli, and also will scale the string coupling accordingly. Now, for an emergence computations, there are 2 points to be understood. First point is which states enter the loop integrals. Second point is how to regularize possible divergences. The first point was addressed by Ralph, so I will not repeat it. I will just state the result. We will include, in principle, D0 branes, towers of D0 branes, wrapped D2 and S5 branes, bound states thereof, and Kaluza-Klein momentum. The second point will be the topic of this last part of the talk. And essentially, in one sentence, that we found a regularization which gives an exact emergence in a certain setup in this limit. Okay, so before going to the actual computation, let me discuss a few technical challenges which actually lead us to a simplification. In principle, if we follow our recipe, we should include an NS5 brains. NS5 brains in this setup are wrapped in such a way to give strings, and it was not clear to us how to integrate out those NS5 strings. As Ralph mentioned, however, this is not so bad because NS5 do not couple to what will be the central charge that will enter, as I will show you. So they will at most contribute as an overall factor in integrals, so in front of the integral, which can be possibly divergent. So you might have to find a regularization for this. And anyway, from emergent string limits, it is expected that they contribute. So, I mean, these are an open question still. Another complication comes from the fact that in principle, in a generic setup, you can have another infinite contribution coming from the sum over all infinitely many wrapping D2 brains. So you have
Niccolò,
yes.
Can I ask a quick question?
Yes.
So it's about the NS5 brains. Since they're strongly
Yes.
coupled, right? You know, because you're in a perturbative setup, you might expect they don't contribute. You know, we usually sum over weakly coupled towers, right? So
Yes. So yes, they don't contribute to the species scale for sure. But I mean, since they are at the same scale as the D2 brains, I don't. In principle,
I know the mass case is similar, but they're
Yes.
not weakly coupled, right?
Yes, I agree. Yes,
Okay.
Yes. Just we don't have a stronger argument than this. Yes, so we were open-minded for this reason.
But you could say the same for the heterotic string that I was presenting, and there it definitely contributes. Because in the dual picture, it contributes. The heterotic string excitations do contribute to the coupling.
I guess one then should identify for this NS5 brains what is the perturbative coupling, right? Like, so these strings in the other frame, they become perturbative. That's why, you know, they contribute.
Yeah, of course. Then we have the perturbative description, and then we know what to do. But I agree. We don't know. We don't know what happens. But just by analogy, I think there is no reason why they a priori should be excluded from the very beginning.
Right. Thanks.
Welcome.
Yes. And okay, and then as I was saying, there is also there are in principle an infinite coming from D2 brains, and they do enter loop integrals as particles. They couple to the mass spectrum. So in principle, these are there. So still, to make progress and to give evidence, we decided to do a simplification, which can avoid all of these obstructions. And the simplification is essentially to consider what is called the resolved conifold. So this is a model with just a single kernel modulus for which the result is known. So what we are going to compute is known. So we have something to compare with. And so we'll be focusing on F0, what is called the prepotential, and F1 is the genus 1 topological steering free energy, let's say. And the full expressions are known. So there is a constant term in the prepotential, a cubic term, and then there is a full series. So these are a 3 logarithm function. Whenever you will see this kind of function, so the generic definition is this. It's just a condensed way to put together instanton corrections. So these are just non-perturbative corrections, and there are other non-perturbative corrections, so at genus 1 here. And there is a linear term as well at genus 1. So this is the full result known via other methods, and we want to reproduce this. Now, in this model, there is just single 2-cycle sphere, and meaning there is a single D2 brain. So we avoid that problem of infinitely many wrapped in D2 brains, and there are no 4 cycles. So the NS5 will not contribute in this specific model. So this is just a clean setup in which to perform a first test of emergence, and this is what we are going to do next. So the question is whether or not we can, via loop integrals, reproduce precisely this result, or up to what extent we can reproduce this result. Okay, so this is the computation I'm going to show next. So the starting point are Schwinger-like integrals. There are 2 integrals to be computed, and then there is a sum over the full spectrum. So the integrals have this structure. There is a Schwinger parameter here, S, and then there is an exponential of the mass spectrum. I will be considering BPS states. So the mass of BPS states is the central charge of the supersymmetry algebra. In this case, it takes this form. There is a linear term, and then there are the KK levels. an integer, which are the KK levels. Now, the fact that this starting point is actually highly non-trivial, it's related to the fact that these quantities are topological string-free energy. So this is a very specific situation in which there is a very nice starting point. In general, the situation might be different, so you might not have this nice expression to start with. And you might see that there is a difference. I mean, this will not play much role eventually, but just to explain this, there is a difference in the powers of the Schunker parameter. And this can be explained with the fact that these expressions are defined in a theory with a background gauge field. So there is a long story behind, there is a very technical calculation performed in this paper, but the message is that instead of integrating out superparticles, so full supermultiplet, we can integrate out scalars, so spin zero particles in a background field, and the background field is what will change the power. Okay. So before doing the computation, let me show you the strategy which we believe is not working smoothly. So this is the strategy in which you cut the sum off at a certain level. This is natural from a QFT approach because you might not want to include in loop integral states which are beyond the cutoff. However, if you do so, let's say you have these integrals and instead of summing over the full integers, you stop at certain level n species. Then you can perform the sum and the integrals because you don't have divergences. If you do it, you get some result. Let's take F0, for example, the prepotential, and you expand it for large T, you get this term. Now, this term, there is a cubic term, which is not so bad because you want to have a cubic term in F0. However, there are a few problems. First of all, this term, there is a small t here, meaning it's the real part of the complex field. So this term is not holomorphic, while F0 must be holomorphic due to supersymmetry. It cannot be not holomorphic. And moreover, the coefficient is also not matching. So there is this coefficient which is different from the known result. And then there are further problems I'm not showing you here, but in these dots, there are hidden other terms which are not matching the known result, either because they have the wrong coefficient or because they are really not there in the known result. And this happens both for perturbative and non-perturbative terms. And also there are other non-holomorphic terms appearing in these dots. So to us, it was not clear how to make sense of this. So maybe there is the possibility that you can cure all of this problem at once, but it was not clear to us how to proceed in this respect. And a posteriori, since the computation I'm going to show you next is giving directly the expected result, we believe that this is teaching us that this strategy of cutting the sum off at a certain level is not the correct one to get the exact emergence. Okay, so then what to do? The strategy is the following. We take the Schwinger integral and we regularize it because these integrals are in principle divergent in the UV. Then we first integrate over the Schwinger parameter and then we perform the infinite sum with a zeta function regularization. So let me start with F1 for F1, which is simpler.
So Niccolò, can I ask
Yes.
a quick question?
Sure.
Do you have any further justification for zeta function regularization other than it gives the correct result?
Because you include automatically an infinite tower with that. I mean, it's like you're summing over infinite states.
But for instance, there were these papers by Thomas Grimm and Pierre Corvillan and Diego Regalado where they were competing something else, right? But they were competing, for instance, one loop Chern-Simons terms. And
Okay.
the whole point of those papers, which was kind of surprising to me at the time, was that zeta function regularization was giving the wrong result. So in that case, they had to look at a different regularization, which was also summing over an infinite tower, but in a different way. So it's very interesting that zeta function seems to give the correct result here, but I just wanted to know if there's any further intuition of that. I mean, it's good enough that it gives the right result, but yeah. Okay.
Beside the fact that it's an infinite number of terms, no, I should check that paper again to see if I can spot the difference. As of now, I cannot say more.
I guess somehow,
Okay, so,
like
yes.
when you get the wrong result is because you are not, like the regularization is not consistent with the symmetries of the higher dimensional theory. Like in those papers, it was not consistent with gauge invariance, so they were using polybillars. Probably here, I don't know. Luckily, this regularization is still consistent with the symmetries, no, of the higher dimensional theory, and maybe it's fine. But yeah,
that could be yes. Thanks. Okay, so very briefly, there are two contributions because, as I said, we have towers of D0 and bound states of D0, D2 branes. So every time I will have to calculate those two contributions independently for F0 and F1. I will start from F1. The pure D0 brane tower is the simplest contribution you can calculate. It's actually a direct computation. And you will find a term which is a logarithmic divergence with mu is containing the cutoff of the Schwinger integral. So since this is a constant term, it's not so bad because you can just subtract the divergence. This is done also in other similar computations in other frameworks. So we take this as a defining procedure for our regularization scheme. And then the most interesting part is the other one. So the tower of D0, D2 branes. Now we split the sum into different pieces. And let's look at the red piece here. This piece can be rewritten with an identity for these functions. You can rewrite this infinite sum with a linear term, a logarithmic term, and then there is this polylogarithm function, which are always non-perturbative contributions. Then the blue terms are easier because you can just use zeta function regularization for this. If you do it, there will be some zero, some terms which are vanishing, coming out, and some other terms, which I'm not writing down, but those terms coming out from these blue terms will combine with this black term here and this one in order to cancel in such a way that eventually just are left with the linear term here and the non-perturbative term here. And these are coming out precisely with the same coefficient I showed you before. So these are direct and clean computation in which we can reproduce both perturbative and non-perturbative contribution to F1. Okay, so F0 is a bit more subtle. We'll sketch the computation. Again, there are two contributions, pure D0 tower and D0 D2 towers. As always, the pure D0 contribution is simpler, and it gives us a constant. This time is a finite constant, and is actually the correct constant you find in the known result. So this zeta 3. You use zeta function regularization, you will see that this infinite sum can be written as zeta 3. And these are holomorphic terms. So we are avoiding, in this case, the problem of non-holomorphicity. The F0, D0, D2 branes contribution is actually the most interesting, I think, and is perhaps the less simple to calculate. So we split it in this way. So there are two kind of terms, the blue ones and the red ones. The red ones are easier. You just use zeta function regularization and it will produce something. The blue ones are a bit more involved, but if you look at them, you can recognize that these can be rewritten as a certain combination of prime derivatives of what is called the Hurwitz zeta function, which is just a generalization of the Riemann zeta, which is centered not at 0, but at some point, complex point it in this case, then minus it. Now, whenever you look into the math literature for properties of these functions and derivatives of this function, you will see that, I mean, it's very complicated to find identities expressing derivatives actually of these functions in a nice way. So with function you can deal with. And actually, this is the case for this particular combination. If there was a minus here, I think this was not the case. This one was not going to work. Or if the coefficient was not 1, this was not so simple. Really, because there is this specific combination, there is a precise mathematical identity, which is rewriting this combination with in terms of a Bernoulli polynomial, which is a polynomial of degree 3 in the argument, a 3 logarithm function, and then there is an additional contribution. This additional contribution will cancel out with the red terms in such a way that, and with some terms here in the Bernoulli polynomial, in such a way that you are left with precisely a cubic term and a full non-perturbative contribution. And again, the coefficients are exactly those which are known to be in the conifold expression. So here I'm not tuning any coefficient, I'm just following the calculation and keeping track of all signs and factors of pi and so on. So to summarize, putting everything together, F0 and F1 are split into two contributions, pure D0 branes tower and bound states of D0, D2 branes. And we just perform the computation and we find precisely a constant term, a cubic term, and a non-perturbative contribution, which are the full set of instaton corrections in this case. And the same happens for F1. There is a linear term and a non-perturbative contribution. And this result matches exactly with the conifold expressions. So we believe that this gives a proof of principle that exact emergence can be realized in this setups, in this framework, in this corner of string theory, and for this kind of limits. To summarize,
yes. Well, sorry, if you're finished, I can wait. Sorry.
No, please.
No, I just wanted to ask. You were doing one modulus. Presumably, if you're getting the cubic piece of the potential, if you do it with several moduli, you should be able to get like triple intersections and stuff.
Yes.
Right. So that should also come out of calculations like this of zeta function regularizations. Is that the picture?
We don't know. So yes, that's the.
But that would be the picture, I guess. Yeah.
Yes, probably yes, because that will come from these infinity two branes probably that you have to sum over them. There are infinitely many of them, so hopefully yes. But we started thinking about that, but we don't have an answer for the moment.
And this is because it's like I could picture this as non-compact conical, right? So there's no really gravity,
yes.
sort of, in some sense.
Yes.
Okay.
Yes. I mean, I'm not.
I'm asking if I could think of this as a calculation just for the non-compact conical, in which case there would be no, for the gravity.
Well, you can do like that. Yes. Also, I think there is
and it will work. It will work out similarly.
For topological coupling, probably yes.
Yeah, right. The question is whether the modulus is really dynamical or not, like in the non-compact stuff, it's just frozen. But okay. All right, thanks.
I think I'm not understanding. The non-compact case, cubic term is not well posed mathematically. What are we asking here? I'm not sure what you're asking.
I didn't get, sorry.
There's ambiguities in the cubic term.
Why there is an ambiguity in the cubic term?
In the non-compact case, if you try to define the triple intersection, it's not a well-posed.
Okay. Yes. Fine. Okay.
Therefore, what are we talking about? I'm confused.
In that case, you would do a compact Calabi-Yau. Yes. Okay.
So I'm not sure what you mean as evidence here, really. Evidence for what? The problem is the cubic term, really. My only problem is cubic term. And so this is not going to prove that question.
Well, I'm not sure I understand.
Okay,
maybe we can talk later about this. Yes. So I just finished very briefly. Okay, so essentially the logic was that we compute the species scale in the limit of interest. So you in principle have the full answer, you compute the limit of interest. Then you determine which towers are light with respect to the species scale, and then you integrate them out in loop intervals. As Ralph already mentioned, so we'll not discuss this since I'm out of time. You can try to do the same in other dimensions, in particular for critical string theory, and this will lead you to possibly a proposal for a perturbative definition of M theory on a circle. And to conclude, so emergence has been proposed as a fundamental property of quantum gravity, and if confirmed, this will be a new tool for investigation, so to calculate effective actions or to study quantum gravity more in general. And the precise formulation of the emergence proposal is still not clear in string theory, so it's an open question. And as Ralph argued, it is likely not easy to realize in emergent string limits, at least not in a standard, in a straightforward way. And on the other hand, it is possibly realized in the compactification limits. So if then this evidence will be confirmed, this will be let's say a proof of principle that emergence can be a property of M theory, so of this particular current of quantum gravity. And in particular, these results would support the idea that the emergence proposal, distance conjecture, and the species scale are mutually connected, so they are essentially all part of a unique thing, and you should study all of them together. Then as future direction, I think the role of the NS5 brane is important to be clarified because we are not sure yet on how to include them precisely in this setup. One can try to do a systematic investigation in other limits in Kähler modularized space, or to perform similar computations in higher dimensions. And finally, since what I showed, what I used was mainly due to supersymmetry, I think it's a fair question whether or not this structure is really fundamentally tied to supersymmetry, or if there are calculations we can do without supersymmetry, which can lead to similar results. And related to this, let me just mention briefly that we are organizing a workshop on non-supersymmetric strings next week. You can attend online, and you're welcome to register, and we will be happy to see you there. So thank you for your attention.